Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with volcanic lightning, the power of static in the ash clouds. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. An intricate interplay of natural forces gives rise to this captivating phenomenon. Volcanic lightning occurs within the towering plumes of ash and gas ejected during eruptions. This region, rich in charged particles, becomes a conduit for electrical discharges. Ash particles collide and fragment, generating static electricity. The resulting charge separation leads to the formation of lightning bolts that arc within the ash cloud, or from the cloud to the ground. These phenomena have been recorded in numerous volcanic eruptions, showcasing their connection to explosive volcanic activity. The energy released during an eruption, combined with the turbulent conditions within the plume, creates an environment conducive to electrical discharge. Lightning strikes can illuminate the ash cloud, offering a brief glimpse into the chaotic dynamics at play. The frequency and intensity of these lightning events can vary significantly. Some eruptions generate hundreds of strikes per minute, while others may produce only sporadic flashes. This variability is influenced by several factors, including the composition of the erupted materials, the height of the ash plume, and the prevailing atmospheric conditions. Understanding these electrical discharges provides valuable insight into the processes occurring during an eruption. Researchers continue to study the mechanisms behind volcanic lightning, seeking to unravel the complexities of this natural phenomenon and its implications for volcanic monitoring and hazard assessment. Historical accounts of volcanic lightning provide a fascinating glimpse into humanity's long-standing fascination with this phenomenon. Ancient texts often describe fiery displays illuminating the skies above erupting volcanoes, suggesting that these events have captured human attention for millennia. Observers from various cultures documented their experiences, interpreting the lightning as omens or messages from deities. In the early 18th century, scientific inquiry began to weave itself into these accounts. Naturalists and explorers, equipped with rudimentary tools, recorded the occurrences of lightning during volcanic eruptions, noting the association with ash clouds and pyroclastic flows. The eruption of Mount Vesuvius in 79 AD inspired vivid descriptions of luminous phenomena, while the eruption of Krakatoa in 1883 prompted international observation efforts, capturing both the sound and light generated by the volcanic activity. Accounts from the 19th century shed more light on the characteristics of volcanic lightning, clarifying its relationship to the electrical charges generated by the ash and gas released during eruptions. Observations from observers on site and distant observers contributed to a growing body of knowledge, linking electrical activity to volcanic eruptions more systematically. These historical perspectives not only illustrate the awe inspired by volcanic lightning, but also reflect humanity's evolving understanding of the natural world, laying a foundation for contemporary research in atmospheric science and volcanology. Static electricity arises from the imbalance of electric charges within a material or between materials. When two surfaces come into contact and then separate, electrons can transfer from one surface to another, leading to a buildup of charge. This phenomenon is particularly relevant in environments where particles are abundant, such as ash clouds produced by volcanic eruptions. The collisions between ash particles, water droplets, and gas molecules create conditions ripe for charge separation. In volcanic contexts, the rapid ascent of volcanic gases and ash generates immense friction. This frictional interaction facilitates the separation and accumulation of electric charges, leading to the development of powerful electric fields. When these fields grow strong enough, they can overcome the insulating properties of the surrounding atmosphere, resulting in electrical discharges. These discharges manifest as lightning, illuminating the dense ash clouds with brief flashes of light. The formation of volcanic lightning is not solely dependent on the ash and gases emitted during eruptions. Atmospheric conditions, such as humidity and temperature, also play critical roles. The presence of moisture can enhance the conductivity of the particles within the cloud, further promoting the generation of static electricity. This intricate interplay between physical processes underscores the complexity of volcanic phenomena and their effects on atmospheric dynamics. The mechanics behind explosive events are rooted in the interactions among heat, pressure, and gas within a volcano's magma chamber. When magma rises towards the surface, its ascent generates increasing pressure, leading to the accumulation of volatile gases. These gases, primarily water vapor, carbon dioxide, and sulfur dioxide, dissolve into the molten rock at high pressures. As it nears the surface, pressure decreases, allowing these gases to expand rapidly. This expansion creates bubbles that coalesce, leading to a buildup of force. When the pressure surpasses the strength of the surrounding rock, an eruption occurs. The release of this pressure can result in a variety of explosive behaviors, from gentle lava flows to violent eruptions characterized by pyroclastic flows and ash clouds. Ash and volcanic debris can be ejected hundreds to thousands of meters into the atmosphere, forming extensive plumes that influence local weather patterns. Interactions between the ejected materials and atmospheric conditions can lead to phenomena such as volcanic lightning, where static electricity generated by ash particles colliding creates dazzling displays. The fallout can have significant consequences, affecting air travel, climate, and ecosystems for miles around. The effects of these eruptions serve as a reminder of the dynamic nature of the Earth's geology and its influence on the atmosphere. Electrical charges begin to accumulate within the ash clouds, driven by the friction generated as particles collide. This turbulent interaction leads to the generation of static electricity, with fine ash particles gaining positive charges, while larger fragments acquire negative charges. The distribution of these charges creates a complex electric field within the volcanic plume, aiding the formation of lightning. These ash particles, often glassy and sharp-edged, play a crucial role in the process. Their varied sizes and shapes influence how they interact with one another, affecting the overall charge separation. In this region, the movement of these particles can lead to the rapid discharge of energy, creating spectacular displays of volcanic lightning. Observations reveal that this phenomenon is not limited to large eruptions. Even smaller events can produce electrical activity. The presence of moisture within the ash clouds can further augment the electrical properties, enhancing the likelihood of lightning strikes. Each flash illuminates the ash clouds, forming bright arcs that showcase the latent energy within these otherwise opaque formations. The study of volcanic lightning provides insight into the conditions present during an eruption, offering clues about the mechanisms driving these natural occurrences. Understanding this phenomenon adds depth to our knowledge of both volcanology and atmospheric science, highlighting the intricate connections between geological processes and electrical phenomena in the atmosphere. The formation of ash clouds begins with explosive volcanic eruptions, where molten rock, gases, and ash are violently expelled into the atmosphere. These eruptions can generate immense plumes that rise several kilometers above the surface, propelled by the force of expanding gases. Within these plumes, the particles of ash interact with one another, creating a complex mixture of fine dust, larger fragments, and vapor. As the ash particles ascend, they collide and fragment, increasing in surface area. This process, known as aggregation, plays a crucial role in the dynamics of ash cloud formation. The finer particles are carried higher into the atmosphere, where they can be transported over vast distances by prevailing winds. This region becomes a chaotic environment, with turbulent eddies and varying temperatures influencing the movement of the ash. Electrical charges accumulate as the particles collide, leading to the development of static electricity within the cloud. These charges can result in volcanic lightning, a manifestation of the electrical activity that occurs during eruptions. The ash clouds themselves can persist for hours or even days, depending on atmospheric conditions, dispersing ash and gases far from the eruption site. Their impact on aviation and climate, through cooling effects and reduced visibility, underscores the significance of understanding these processes and dynamics in the context of both natural events and human activity. The classification of volcanic eruptions provides insight into their mechanisms and the resulting phenomena. Strombolian eruptions are characterized by their relatively mild explosiveness, often producing short bursts of lava and ash. These eruptions create rhythmic explosions, sending glowing lava bombs into the sky. The continuous ejection of material results in the formation of a cone-shaped structure, reflecting the steady yet dynamic nature of such events. In contrast, Plinian eruptions are marked by their violent and sustained explosive activity. These eruptions generate towering columns of ash and gas that can reach several kilometers into the atmosphere. The sheer volume of material expelled can lead to significant pyroclastic flows which travel rapidly down the flanks of the volcano, reshaping the landscape. The aftermath of these eruptions can result in long-lasting climatic effects due to the substantial ash clouds that may linger in the stratosphere. Beyond these two types, fissure eruptions occur along cracks in the Earth's surface, producing extensive lava flows that can reshape vast regions. Each eruption type holds unique characteristics, influenced by factors such as magma composition, gas content, and tectonic settings. Understanding these distinctions enhances the ability to predict volcanic behavior and mitigate potential hazards associated with eruptions. This knowledge remains crucial for both public safety and scientific inquiry into the Earth's dynamic processes. The relationship between ash composition and electric charge plays a significant role in understanding volcanic lightning. Different minerals present in volcanic ash contribute to the generation of electric charges as they interact during eruptions. For instance, silica-rich ash tends to create distinct electrical properties compared to basaltic ash, which is less viscous. This variance affects the way particles collide and fragment, resulting in varying degrees of charge buildup. Observations indicate that the size and shape of ash particles, also influence their ability to generate static electricity. Angular particles tend to exhibit higher charging efficiency than rounded grains, as their edges create more opportunities for collisions that transfer charge. In this region, the presence of moisture further complicates the dynamics, facilitating the flow of electric current through the ash cloud. When eruptions occur, these charged particles can influence the surrounding atmospheric conditions, leading to the formation of lightnings. The discharge of electricity through volcanic plumes can occur in multiple forms, such as intra-cloud and cloud-to-ground lightnings. This phenomenon not only illuminates the ash clouds, but serves as an indicator of the energetic processes at play within the eruption itself. The intricate interplay of ash composition, particle size, and environmental conditions continues to be an area of research, revealing the complex behaviors of volcanic systems and their associated electrical phenomena. Water vapor plays a critical role in volcanic eruptions, influencing both the dynamics of the eruption and the characteristics of the emitted materials. It acts as a primary driving force during various stages of volcanic activity. When water trapped within magma is subjected to extreme pressure, it can rapidly vaporize, leading to explosive decompression. This sudden release of gas contributes to the fragmentation of magma, generating ash and pyroclastic flows that can dramatically alter the surrounding landscape. In addition, the presence of water vapor affects the temperature and viscosity of magma. Higher water content typically reduces viscosity, allowing for a more fluid-like behavior. This fluidity can facilitate the movement of magma through subterranean pathways. The interaction between water vapor and other volcanic gases, such as sulfur dioxide, can also influence atmospheric conditions. This region may experience changes in air quality and temperature, impacting local ecosystems. The release of steam during eruptions adds another layer of complexity, contributing to the formation of volcanic clouds that can extend across vast distances. Understanding the role of water vapor enhances comprehension of the intricate processes that govern volcanic behavior and their environmental ramifications. The expansion of steam and gases during an eruption initiates the formation of a convective column. Rising heat causes the surrounding air to become less dense, creating a powerful upward force. This phenomenon drives the column skyward, pulling ash and debris along with it. The interaction between the ascending materials and the cooler air above leads to a complex array of temperatures, enabling the generation of static electricity. As particles collide within this tumultuous environment, they lose or gain electrons, resulting in the accumulation of electrical charge. When the charge reaches a critical threshold, it is released in the form of lightnings, manifesting as brilliant flashes amid the ash clouds. This electrical discharge serves to illuminate the darkened skies, forging a vivid contrast against the backdrop of volcanic activity. The presence of volcanic lightning signifies not only the intensity of the eruption, but also the intricate dynamics at play within the convective column. Each strike reveals the ongoing interactions of chemistry and physics, highlighting the delicate balance sustaining these explosive phenomena. This region, marked by its turbulent atmosphere, embodies the raw power of nature, while serving as a reminder of the profound complexities inherent in volcanic systems. The interplay of heat, moisture, and electrical forces continues to captivate researchers seeking to unravel the mysteries of Earth's dynamic processes. Mesipshij within volcanic clouds are generated through a series of complex interactions. As volcanic eruptions propel ash and gas into the atmosphere, the collision of particles occurs at high velocities. These collisions result in the transfer of electrons, leading to regions of differing electrical charge. The turbulence of rising ash and gases contributes to the ongoing separation of charges. Larger particles, often composed of silicate minerals, tend to acquire a positive charge, while the finer particles remain negatively charged. This segregation creates an electric field strong enough to initiate discharges. As the eruption plume rises, moisture within the volcanic gases plays a crucial role. Water droplets form around ash particles, enhancing the charge separation process. When these droplets collide and coalesce, they facilitate the transfer of charge, amplifying the existing electrical differences. This phenomenon is further influenced by atmospheric conditions. The presence of humidity can increase conductivity, allowing the charges to build to greater levels. Once the threshold is reached, the energy is released in the form of lightnings. Each flash illuminates the ash-filled sky, revealing the chaotic dance of particles caught within the shifting cloud. Such events represent a fascinating intersection of geological and atmospheric science, shedding light on the intricacies of nature's processes and their far-reaching implications. Electrostatic forces in nature manifest in various forms, illustrating the interconnectedness of different phenomena. In this region, volcanic activity generates immense heat, causing the rapid rise of ash and gas. These particles collide, leading to the transfer of charge and the buildup of electricity within the volcanic plume. This process mirrors the mechanisms observed in thunderstorm formations, where moisture-laden air ascends, creating conditions ripe for electrical discharge. In both scenarios, the resulting electrostatic forces can reach a threshold, producing dramatic displays. Lightning within a thunderstorm occurs when the accumulated charge is released, while volcanic lightning illuminates the ash-laden sky during an eruption. Each event serves as a reminder of the power of nature's forces and their ability to reshape landscapes and atmospheres alike. Beyond these spectacular displays, the implications for the surrounding environment are profound. The presence of electrical discharges can influence local weather patterns, altering precipitation and temperature distributions. Such changes can have cascading effects on ecosystems, impacting flora and fauna. The study of these phenomena not only enhances understanding of volcanic activity, but also contributes to meteorological science. By examining the similarities and differences in electrostatic phenomena across various conditions, researchers gain deeper insights into the fundamental principles governing atmospheric behavior. The eruption of Laki in 1783 serves as a compelling case study in volcanic phenomena and electrical behavior. This event released vast quantities of ash and gas into the atmosphere, creating an environment ripe for electrostatic activity. During the eruption, observers noted striking displays of volcanic lightnings where charged particles collided within the tumultuous clouds, discharging energy in the form of brilliant arcs. The power of this natural phenomenon is illustrated by the sheer number of lightning strikes recorded, with estimates suggesting thousands occurred within a short time frame. The ash clouds, laden with volcanic material, played a crucial role in facilitating these discharges, with the presence of ice and moisture aiding in charge separation. It became evident that these atmospheric conditions were ideal for creating significant electrical activity. The aftermath of the eruption not only altered the landscape but also affected weather patterns across vast regions. The release of sulfur dioxide led to climatic changes that resulted in cooler temperatures, illustrating the interconnectedness of geological events and atmospheric conditions. This interplay between ash and electricity highlights the complexity of volcanic eruptions, demonstrating the power of nature in both its beauty and its potential for destruction. Such instances remind us of the intricate relationships that govern our planet's systems, each event revealing deeper truths about the forces at play in the Earth's atmosphere. The interplay of particle size distribution significantly influences charge dynamics within volcanic ash clouds. Variations in particle dimensions lead to differing interaction mechanisms. As these particles collide and aggregate, larger particles, while less abundant, contribute to a significant portion of the electrical conductivity, while smaller particles, although more numerous, enhance the overall charge transfer through more frequent collisions. As the eruption commences, the immediate environment becomes charged through friction and contact electrification. This phenomenon can generate static electricity, creating a buildup of potential that may eventually discharge as lightnings. The specific size range of the ash particles determines the efficiency of this process. For instance, particles measuring between 1 and 10 micrometers exhibit optimal conditions for charge separation, facilitating the accumulation of energy within the cloud. The behavior of these particles is influenced by their composition, surface texture, and moisture content. Variations in these characteristics can alter the conductivity of the ash cloud, leading to changes in the frequency and intensity of volcanic lightnings. Each eruption, unique in its particle composition and environmental conditions, contributes to a broader understanding of these interactions. Observations of these phenomena provide invaluable insights into the underlying processes that govern both volcanic activity and atmospheric electricity. Wind patterns exert a significant influence on the behavior of ash clouds, shaping their dispersion and concentration in the atmosphere. Variations in wind speed and direction can stretch these clouds over vast distances or cause them to accumulate in localized areas, impacting both air quality and aviation safety. The interaction between volcanic eruptions and prevailing winds can trigger complex dynamics, leading to the formation of distinct ash plumes. These plumes, often buoyed by the heat of the eruption, ascend into the upper atmosphere, where they encounter diverse wind currents. This interplay can create elongated shapes, with ash particles being transported hundreds of kilometers away from their source. In some instances, the ash may even ascend into the stratosphere, where it can influence climate patterns by reflecting sunlight and altering atmospheric temperatures. The study of these interactions reveals the vital role of meteorology in understanding volcanic events. Various models simulate how wind patterns affect the trajectory and thickness of ash clouds, providing crucial information for disaster response efforts. Observations indicate that regions downwind from active volcanoes may experience significant ash fallout, leading to potential health hazards and disruptions to infrastructure. Continued research into this relationship contributes to our broader understanding of both volcanic processes and atmospheric dynamics, reinforcing the interconnectedness of Earth systems. Temperature plays a crucial role in the formation of volcanic lightnings, influencing the electrostatic conditions within ash clouds. As magma rises to the surface, it generates intense heat, which subsequently leads to the rapid expansion of gases and the fragmentation of volcanic material. This process creates fine ash particles that become electrified. Higher temperatures within the eruption column intensify this phenomenon, enhancing the collision frequency among ash particles. The ash cloud's composition is equally significant. Varying mineral contents can alter electrical properties. Silica-rich materials, when fragmented,
tend to generate more static electricity than other compositions. These electrical charges accumulate as particles collide and interact. In terms of atmospheric conditions, the surrounding environment plays a vital role in the manifestation of volcanic lightning.
Atmospheric moisture content and temperature inversions can enhance the likelihood of electrical discharges, resulting in vivid lightning displays. Observations during eruptions show that temperature not only facilitates the initial formation of ash clouds, but also sustains the dynamic processes that lead to this unique atmospheric phenomenon. Understanding these interactions helps clarify the intricate relationships between volcanic activity and atmospheric behavior. The connection between volcanic eruptions and thunderstorms reveals a fascinating interplay of forces. Eruptions release vast amounts of ash and gas into the atmosphere, creating a charged environment. This region becomes ripe for electrical activity, as particles collide and generate static electricity. The particles, propelled by the upward surge of the eruption, finish istar of electricity. The particles, propelled by the upward surge of the eruption, rise into the atmosphere, forming a turbulent cloud that can extend for miles. Within this cloud, the conditions mirror those found in typical thunderstorm development. The presence of moisture, coupled with the high altitude and the strong updrafts, allows for the formation of ice crystals. As these ice crystals collide with ash particles, they become positively or negatively charged, leading to the buildup of electrical potential. Eventually, this accumulated charge can discharge in the form of volcanic lightning, striking through the ash-laden skies. The presence of this lightning serves as a striking indicator of the eruption's intensity and the dynamics of the ash cloud. It illustrates not only the immediate atmospheric effects of volcanic activity, but also highlights the broader implications for weather patterns. These phenomena can influence local climate, altering precipitation and temperature patterns long after the initial eruption has subsided. In understanding these connections, researchers can gain insights into the complex interactions that shape our planet's atmosphere. Sheet lightning manifests as a diffuse glow, illuminating the ash clouds, creating a soft, luminous veil against the darkened sky. This phenomenon occurs when electrical discharges travel through the volcanic ash, forming a continuous flash that can stretch across vast distances. The presence of numerous charged particles within the plume facilitates this widespread illumination, revealing the typically invisible forces at play within the turbulent atmosphere. In contrast, forked lightning presents a more jagged and dynamic appearance. This type of discharge occurs when the electrical energy follows a more chaotic path, branching out and darting across the ash-laden sky. The intricate patterns resemble the fractal nature of natural forms, showcasing the unpredictable behavior of electrical currents as they interact with the dense particles of ash. Each fork represents a momentary release of energy, illuminating the surrounding darkness with sharp, brilliant flashes. Staccato lightning, characterized by its abrupt and sporadic bursts, adds yet another dimension to this atmospheric spectacle. These brief, intense discharges occur in rapid succession, creating a flickering effect within the clouds. The rapid succession of flashes reveals the volatility of the charged environment as energy builds and releases in quick bursts. Each type of volcanic lightning contributes to the ongoing study of electrical phenomena, offering crucial insights into the processes that govern our planet's atmosphere. Observational techniques for detecting volcanic lightning are essential for understanding its formation and behavior. Researchers employ a variety of methods, including high-speed cameras and specialized sensors. High-speed cameras capture rapid flashes, providing a time-resolved view of lightning events within ash clouds. These images reveal the intricate details of electrical discharges, helping scientists analyze the frequency and intensity of the phenomena. In addition to visual measurements, ground-based lightning detection networks play a pivotal role. These systems utilize a series of strategically placed sensors that can triangulate the location of electrical discharges. By analyzing the data collected, researchers can map the spatial distribution of volcanic lightning over time. This information aids in correlating lightning occurrences with volcanic activity, enhancing predictions of eruptions. Remote sensing techniques, such as satellite observations, offer another layer of insight. Satellites equipped with infrared and optical sensors can monitor ash plumes and accompanying lightning, providing a broader perspective on volcanic events. Such data contribute to understanding the atmospheric conditions that facilitate lightning generation in volcanic eruptions. The combination of these observational techniques presents a comprehensive approach to studying volcanic lightning. Through meticulous analysis, researchers can decode the complexities of these electrical phenomena, deepening our knowledge of the interplay between volcanic activity and atmospheric dynamics. This ongoing research holds significant implications for both volcanology and atmospheric science. The advancement of lightning detection networks has become essential in understanding volcanic activity. These systems monitor electrical discharges that occur in conjunction with explosive eruptions, contributing valuable data to the field. By capturing the frequency, intensity, and location of lightning strikes, researchers can correlate these phenomena with eruptions and ash cloud dynamics. Detection networks employ a variety of technologies, including ground-based sensors and satellite observations. Ground-based systems utilize triangulation methods to pinpoint lightning events, while satellite systems offer a broader perspective, capturing data over vast areas. This synergy allows for a comprehensive understanding of the electrical behavior associated with volcanic eruptions. Analyzing the data gathered from these detection networks can reveal patterns that indicate the onset of eruptions. Increased lightning frequency often precedes explosive events, serving as a critical warning sign. This early warning capability enhances not only volcanic monitoring, but also public safety measures in regions prone to eruptions. Additionally, the study of volcanic lightning contributes to the understanding of electrical processes within ash clouds. The interactions between ash particles and atmospheric conditions lead to the generation of static electricity, which creates a spectacular phenomenon known as volcanic lightning. This natural occurrence can manifest within ash clouds, often appearing as jagged, bright streaks illuminating the darkened sky. Photographers and videographers seek to capture these fleeting moments, employing long exposure techniques to reveal the intricate patterns formed by electrical discharges. In this region, the contrast between the glowing ash and the surrounding darkness enhances the visual impact of the lightning, creating scenes of surreal beauty. This stark interplay of light and shadow often reveals the chaotic nature of volcanic activity, providing a glimpse into the raw forces at play. The voltage within these ash clouds can reach levels sufficient to create brilliant flashes, which can be both mesmerizing and daunting. Equipment choices are critical in capturing these events. High-speed cameras document the rapid progression of electrical arcs, while infrared filters can expose heat signatures, revealing details invisible to the naked eye. The result is a collection of images and footage that not only showcases the beauty of volcanic lightning, but also conveys the power and unpredictability inherent in volcanic eruptions. The artistry of these captures lies in the ability to freeze a moment that, in reality, lasts mere seconds, creating a lasting impression of nature's dynamic processes. This endeavor to document volcanic lightning reveals a complex interplay of atmospheric conditions. When a volcano erupts, the rapid ascent of ash and gases generates an environment ripe for electrical activity. The violent turbulence within ash clouds leads to the collision of particles, which in turn creates static electricity. This static buildup can reach significant levels, resulting in discharges that manifest as lightning. The presence of water vapor plays a crucial role in this phenomenon. Humid conditions enhance the likelihood of condensation, leading to the formation of droplets that collide with ash particles. These interactions amplify the electrical charge, further increasing the potential for lightning strikes. Temperature differences within the ash cloud contribute to the overall dynamics, as warmer air rises and cooler air descends, creating a convection cycle that fuels the eruption. The physical characteristics of the ash itself are significant. The size, shape, and composition of the particles influence how effectively they can generate and carry electrical charges. Smaller particles tend to be more mobile, allowing for greater interaction within the cloud. This environment can produce a range of electrical phenomena, from faint glows to intense bursts of light. Understanding these conditions and their contributions to volcanic lightning provides valuable insights into the nature of this captivating and powerful force. Volcanic lightning significantly influences local ecology, particularly in the immediate aftermath of an eruption. The electric discharges emitted during these events create a unique atmospheric ionization, altering the chemical composition of the surrounding air and soil. This modification can lead to increased levels of nitrogen compounds, fostering nutrient availability for various plant species. Enhanced nutrient profiles enable rapid vegetation growth in the wake of ash deposition, contributing to ecological recovery. The intense heat generated by the lightning may also facilitate the ignition of nearby vegetation, resulting in localized fires. While seemingly destructive, these fires play a role in the regeneration process. They can clear out old growth, making space for new plant life to emerge, which often exhibit different characteristics and resilience to subsequent eruptions. Fauna inhabiting these regions adapt to the unique conditions shaped by volcanic activity. Many species evolve to thrive in nutrient-rich soils, while others utilize the altered habitats for foraging or nesting. The dynamic interplay between volcanic lightning and the surrounding ecosystem creates a cycle of destruction and renewal. Within this region, life persists and adapts, demonstrating resilience in the face of powerful natural phenomena. Volcanic gases play a significant role in the formation of lightning during eruptions. These gases, primarily water vapor, carbon dioxide, and sulfur dioxide, are expelled into the atmosphere along with ash and particulate matter. The interaction of these elements creates a highly charged environment. This region, infused with volcanic material, becomes a fertile ground for electrical discharges as particles collide and generate static electricity. The process begins when ash particles are propelled into the air, colliding with one another. These collisions lead to the transfer of electrons, causing some particles to become positively charged, while others acquire a negative charge. The accumulation of these charges within the ash cloud creates an electrical imbalance. Under the right conditions, this imbalance reaches a critical threshold, initiating the discharge of electricity in the form of lightning. The presence of gases enhances this process. Water vapor, in particular, plays a crucial role as it can further ionize the surrounding atmosphere, facilitating the movement of electrical charges. Sulfur dioxide can also contribute to the formation of aerosols, which serve as additional particles for collision. These interactions manifest as vivid flashes illuminating the dark ash clouds, revealing the dynamic interplay of volcanic activity and atmospheric phenomena. Through this intricate process, the power of static electricity emerges as a striking representation of nature's complexity. The composition of ash clouds plays a vital role in the generation of electric charge. Mineral particles, including silicates and oxides, become airborne during explosive volcanic events. These fine particulates, when suspended, interact with one another, resulting in friction and collision. Such interactions induce a transfer of electrons, leading to a buildup of static electricity within the cloud. These ash clouds are rich in volcanic glass, which possesses unique properties ideal for charge generation. They contain various chemicals, such as sulfur dioxide and carbon dioxide, which, upon release, can react with atmospheric moisture. This reaction further influences the electrical properties of the surrounding environment. Water vapor can condense on ash particles, enhancing the conductivity of the cloud and facilitating the flow of electricity. As the electrical charge accumulates, the potential for discharge increases. This can manifest as volcanic lightning, a phenomenon often seen during eruptive events. The discharges may occur within the cloud itself or between the cloud and the volcanic vent, illuminating the sky with brief flashes of light. The presence of ash alters the dynamics of the atmosphere, creating a unique interplay between chemistry and electricity. The interaction of particles within this region not only illustrates the complexities of volcanic activity, but also highlights the interconnectedness of atmospheric processes and geological phenomena. The interplay between ash and ice serves as a critical factor in thunderstorm development. Volcanic ash particles, when dispersed into the atmosphere, become agents of ice nucleation. This process is essential for the formation of ice crystals within storm clouds. In this environment, the presence of ash enhances the likelihood of supercooled water droplets to freeze upon contact, promoting the growth of ice particles. These ice particles, in turn, contribute to the electrification of the storm system. The collision between the ash-laden ice crystals and other atmospheric particles leads to the transfer of electrical charge. This phenomenon is a significant contributor to the generation of lightning within the storm. The characteristics of the ice crystals and their interactions with ash can influence the intensity and frequency of lightning strikes. The intricate relationship between ash and ice not only affects electrical activity, but also impacts precipitation patterns. Enhanced ice formation can lead to increased rainfall, as larger ice particles eventually fall and melt into droplets. This alteration in hydrometeor composition influences the overall dynamics of the storm system. Understanding this interaction sheds light on the broader implications of volcanic eruptions on weather patterns. The resultant thunderstorms can extend far beyond the volcanic region, affecting ecosystems and weather systems on a continental scale. Observations continue to clarify these complex atmospheric connections. Eruption intensity plays a crucial role in determining the frequency of lightning events within ash clouds. Volcanic activity generates substantial amounts of ash and gas, creating an environment rich in charged particles. The more vigorous the eruption, the greater the dispersion of these particles, which contributes to the electrical activity observed. In instances of explosive eruptions, such as those characterized by high eruption columns, the turbulence and rapid ascent of ash significantly enhance collision processes. These collisions lead to a buildup of static electricity, which, when released, manifests as lightning. Observations have shown that eruptions with higher intensity often produce more frequent lightning strikes, illuminating the ash-filled sky. The relationship between eruption dynamics and electrical activity also includes factors such as temperature and moisture content within the cloud. Higher temperatures can facilitate the movement of particles, increasing their kinetic energy and collision rates. Moisture, on the other hand, affects the formation of ice particles, which are instrumental in the generation of electrical charges through freezing processes. The intricate interplay of these elements creates a spectrum of electrical phenomena, varying not only in frequency but also in intensity and duration. Each eruption contributes unique data points, enhancing the understanding of these atmospheric processes and their implications for weather patterns and volcanic hazards. Real-time monitoring of volcanic activity enables scientists to observe phenomena such as volcanic lightning with unprecedented precision. Utilizing advanced satellite technology, ground-based sensors, and drones, researchers can capture the dynamic interactions between ash plumes and electrical discharges. This region, often obscured by dense clouds of ash, becomes a focal point for atmospheric studies, revealing the intricate relationship between volcanic eruptions and the generation of static electricity. Lightning within these ash clouds occurs when particles collide and create friction, resulting in the accumulation of electrical charges. These discharges can manifest in various forms, from single strikes to vast lightning networks illuminating the sky. The ability to detect and analyze these electrical events in real time offers vital insights into the eruption's intensity and potential hazards. The integration of meteorological data further enhances predictive models, allowing scientists to forecast the movement of ash clouds and associated weather patterns. The interplay between volcanic activity and atmospheric conditions can lead to significant impacts on air travel and local ecosystems. As monitoring technology continues to advance, it fosters a deeper understanding of the mechanisms driving these remarkable phenomena. This knowledge not only aids in hazard assessment but also enriches the broader field of atmospheric science, revealing the complexities of our planet's dynamic systems. The integration of drones into the study of volcanic lightning dynamics marks a significant advancement in atmospheric research. These unmanned aerial vehicles provide an unobtrusive means of gathering data in environments that are often too hazardous for human researchers. Equipped with specialized sensors, they can monitor electric fields, collect ash samples, and capture high-resolution imagery of active eruptions. This capability allows for real-time observation of lightning occurrences within ash clouds, offering insights into the underlying mechanisms of this phenomenon. Drones operate at elevations where lightning is most prevalent, navigating through hostile weather conditions while transmitting valuable information back to ground stations. This data collection enhances our understanding of the electrical activities associated with eruptions, revealing patterns that were previously difficult to discern. The precision of drone technology enables researchers to map the distribution of static charge within the ash clouds, elucidating the relationship between particle size, concentration, and electrical discharge. Such investigations are crucial for improving predictive models of volcanic activity and lightning generation. By analyzing the interactions between ash particles and atmospheric conditions, scientists can better comprehend how these elements contribute to the formation of volcanic lightning. The ongoing exploration of these dynamics continues to illuminate the intricate connections between geological events and atmospheric phenomena, expanding our knowledge of Earth's complex systems. Satellite observations play a crucial role in monitoring volcanic ash clouds and associated lightning activity. Equipped with advanced sensors, these instruments provide near real-time data, allowing scientists to track the movement and dispersion of ash particles. This information is vital for understanding the impact of volcanic eruptions on air quality and aviation safety. Measurements from satellites can detect the presence of ash by analyzing the scattering of sunlight and thermal emissions. This capability enables the identification of ash plumes that may extend for thousands of kilometers, affecting regions far from the eruption site. The ability to visualize these clouds lends insight into their composition and density, which are critical factors influencing lightning occurrence. Lightning within ash clouds arises from the collision of charged particles, a process that transforms the atmosphere into an arena of electrical activity. Satellite data contributes to identifying these electrical bursts, documenting their frequency and intensity. The spatial distribution of lightning strikes can reveal underlying patterns linked to volcanic activity, providing a clearer understanding of how eruptions influence electrical phenomena. Integrating satellite observations with ground-based measurements enhances the accuracy of models that predict ash dispersion and lightning behavior. This synergy between observational techniques enriches the scientific community's comprehension of the interactions between geological events and atmospheric processes, fostering a more informed approach to disaster preparedness and mitigation. Volcanic lightning presents a fascinating intersection of immediate atmospheric phenomena and broader climatic implications. It occurs when volcanic eruptions eject ash and gas into the atmosphere, creating conditions for static electricity to accumulate. This process leads to the discharge of energy, manifesting as captivating streaks of lightning among the ash clouds. The short-term impacts can be profound, disrupting air travel and threatening nearby ecosystems. These electrical discharges can also contribute to increased temperatures in localized areas, amplifying the volatile nature of volcanic activity. In contrast, the long-term effects of volcanic lightning on climate are more complex. The particulates and gases released during eruptions can linger in the atmosphere, affecting weather patterns and global temperature over extended periods. Sulfur dioxide, for instance, can form sulfate aerosols, which reflect sunlight and lead to temporary cooling. This interaction between volcanic activity and climate systems underscores the importance of monitoring these events in relation to their atmospheric consequences. Research indicates that while the immediate effects of volcanic lightning might be fleeting, their influence on climate can persist for years. The intricate balance of short-term disruptions and long-term climatic shifts highlights the need for continued study. Understanding these phenomena provides crucial insight into how geological forces intersect with atmospheric dynamics, shaping the environment in both transient and enduring ways. The connection between volcanic activity and atmospheric electricity reveals the intricate interplay between earth and sky. When a volcano erupts, it releases vast amounts of ash and gas into the atmosphere. This material, propelled into the stratosphere, creates an environment rich in particles that can generate electrical charges. Collisions among these particles lead to the buildup of static electricity, resulting in the formation of lightning within the ash clouds. This phenomenon, known as volcanic lightning, occurs in a distinctly different context than typical thunderstorms.
In these ash-laden clouds, the electrical discharges can appear as brilliant flashes, illuminating the darkened sky. The presence of water vapor and the specific size of ash particles play crucial roles in the efficiency of this charge separation process. The visibility of volcanic lightning serves as an indicator of the eruption's intensity and the energy being released. Each flash not only underscores the immediate volatility of the eruption, but also offers insight into the conditions within these towering plumes. Research into these electrical phenomena aids scientists in predicting volcanic behavior and understanding the broader implications for climate and weather patterns. Such knowledge can enhance hazard assessment and inform communities at risk from eruptions. illustrating the profound connections between geological activity and atmospheric conditions. Cultural significance has long accompanied the phenomenon of volcanic lightning. Diverse communities have interpreted these luminous displays as manifestations of the divine of our core, attributing various meanings to their occurrence. In many regions, the presence of lightning amid volcanic eruptions is viewed as a harbinger of change or a signal from the earth itself. This belief often permeates local folklore, weaving narratives that connect the anger of gods to the fury of nature. Indigenous populations have historically observed these events, incorporating them into their spiritual practices. The dramatic flashes create a striking visual contrast against the ash-filled sky, prompting reverence and awe. Rituals may arise, aimed at appeasing deities believed to control the forces of the earth. This interaction between humanity and the natural world fosters a deep relationship, reflecting a desire to understand and coexist with powerful elements. In contemporary times, volcanic lightning continues to inspire artistic expressions as creators seek to capture its ethereal beauty. Photographs and paintings often depict the interplay of light and ash, preserving the fleeting moments of this natural spectacle. Scientific exploration of volcanic lightning also contributes to cultural narratives, highlighting the intersection of art, mythology, and empirical study. Each eruption, with its accompanying display of electricity, reinforces the enduring connection between humanity and the unpredictable forces of nature. The Tijoing Collection Kokipinias, situated near active volcanoes. The discharge of electricity amidst the ash clouds can lead to dangerous conditions, including fires that spread rapidly through the dry vegetation surrounding these areas. These sudden ignitions can devastate ecosystems, threatening both wildlife and human habitation. Ash particles in the atmosphere contribute to the phenomenon, generating electric charges that create violent flashes, often striking structures or individuals unprepared for such events. Communication systems face disruption during eruptions, not only from the ash fallout, but also from electrical interference caused by lightning strikes. This can isolate communities, complicating evacuation efforts and emergency response. The loss of power and communication can lead to chaos, as residents become vulnerable to both the immediate hazards of volcanic activity and the secondary dangers that arise from weakened infrastructures. The unpredictability of lightning during eruptions adds to the anxiety experienced by those living in proximity to volcanoes. The combination of ashfall, gas emissions, and electric discharges creates a multifaceted threat. Preparedness plans must address not only the physical dangers posed by eruptions, but also the psychological impacts of living under the shadow of such relentless natural forces. Awareness and education can significantly mitigate these risks, fostering resilience within vulnerable populations. The 2010 eruption of Eyjafjallajökull serves as a crucial case study in understanding volcanic lightning within ash clouds. This event released enormous quantities of volcanic ash high into the atmosphere, creating conditions conducive to electrical activity. With the eruption, the interaction between ash particles and atmospheric moisture facilitated the buildup of static electricity. As these particles collided and separated, they generated lightning strikes that illuminated the ash-laden skies. Photographs captured during the eruption showcased intricate flashes, revealing a phenomenon rarely witnessed on such a scale. The resulting plumes soared to altitudes of 9 kilometers, where the colder temperatures further intensified the electrical processes at play. A series of volcanic lightning bolts emerged, with some reports indicating up to 1,000 strikes per hour. The sheer energy generated not only presented a captivating spectacle, but also underscored the potential hazards posed by such events. Air traffic was severely impacted, with widespread flight cancellations affecting millions of passengers. Scientific examinations highlighted the importance of these phenomena for understanding the dynamics of volcanic eruptions. The interplay of heat, ash, and moisture during this eruption provided valuable insights into the mechanisms behind volcanic lightning. This knowledge is essential for predicting future events and ensuring safety in regions susceptible to volcanic activity. Ground deformation serves as a significant indicator of volcanic activity, revealing shifts beneath the surface that often precede eruptions. Subtle changes in elevation, measured through advanced techniques such as satellite radar interferometry, can signal the movement of magma within the crust. This movement creates stress along geological faults, leading to various forms of ground displacement. The phenomena observed in this region underscore the importance of continuous monitoring. Even slight swelling or sinking can provide crucial insights into an impending eruption. Researchers analyze these variations meticulously, correlating them with historical eruption patterns and seismic activity. When ground deformation is detected, it often prompts enhanced observation and data collection aimed at deciphering the underlying processes. In many cases, the relationship between ground deformation and volcanic activity is complex. The interplay of pressure and temperature within the magma chamber can result in diverse deformation patterns, necessitating a nuanced understanding of each unique volcanic system. These observations extend beyond mere prediction. They inform evacuation plans and risk assessments, mitigating potential hazards posed to nearby communities. The integration of ground deformation data with other geophysical measurements amplifies the predictive capacity, allowing scientists to formulate more accurate models of volcanic behavior. Such advancements contribute to a deeper understanding of these dynamic natural phenomena. The geophysical properties of volcanic ash reveal a complex interplay of particle size, composition, and behavior within the atmosphere. Ash particles, often less than 1 millimeter in diameter, exhibit a range of shapes from angular fragments to more rounded grains. This variability affects their aerodynamic properties, influencing how they interact with wind currents and atmospheric conditions. And to mesospheric conditions. Compositionally, volcanic ash is primarily composed of silicates with varying concentrations of minerals such as quartz, feldspar, and volcanic glass. These elements contribute to the ash's density and electrical properties, which can lead to the generation of volcanic lightning during explosive eruptions. The turbulence created by the ejected ash can facilitate the collision of particles, resulting in the transfer of electrons and parsia. In addition to providing insight into eruption dynamics, the analysis of ash fallout patterns offers critical information about eruption magnitude and dispersal. This region's topography plays a significant role in determining how and where ash deposits settle, influencing both local ecosystems and human settlements. The fine ash can travel vast distances, affecting air quality and aviation safety, while coarser particles settle closer to the eruption site, shaping the geological landscape. Understanding these geophysical properties is essential for predicting the impact of volcanic events on the environment and human activity. The sound produced during volcanic lightning, often referred to as thunder, originates from the rapid expansion of air heated by the discharge of electricity. This phenomenon generates shock waves that propagate through the atmosphere, creating a distinct auditory experience. The distance between the observer and the source affects the clarity and intensity of the sound, leading to variations that can be both abrupt and lingering. Acoustic measurements reveal that the frequency and intensity of this thunder are influenced by several factors, including temperature, humidity, and the composition of the surrounding volcanic gases. In these regions, the combination of ash and gas can alter sound propagation, leading to a unique acoustic profile that differs markedly from that of conventional thunder during a storm. Notably, the physical characteristics of the surrounding environment play a significant role in sound transmission. The landscape can reflect and refract sound waves, creating echoes and resonances that enhance the auditory experience. This interplay between the volcanic activity and the acoustics of the environment provides valuable data for scientists seeking to understand the nature of these events. Research into the acoustics of volcanic lightning not only enriches knowledge of atmospheric phenomena, but also aids in developing early warning systems, potentially safeguarding communities in proximity to active volcanoes. The magnetic field of the Earth plays a significant role in the dynamics of volcanic lightning. As molten rock erupts, particles are expelled into the atmosphere, where they interact with the magnetic field. This interaction can enhance the generation of electrical discharges, facilitating the formation of lightning within ash clouds. Charged particles colliding during an eruption create conditions conducive to electrical activity. In this region, the magnetic field contributes to the arrangement and movement of these particles. When ash and gas rise, they experience a variety of forces, including those exerted by the magnetic field. This can lead to the accumulation of charge within the plume, creating a potential difference that may result in lightning strikes. The presence of volcanic lightning serves as a visible indicator of the intense energy released during eruptions. It also highlights the interconnectedness of geological and atmospheric processes. Studying these phenomena reveals how variations in the Earth's magnetic field can influence volcanic activity, and conversely, how volcanic eruptions can impact the magnetic environment. Monitoring these interactions provides critical insights into the behavior of volcanoes and their potential hazards. Scientists continue to explore how these intricate relationships affect both the atmosphere and the Earth's surface. The effect of ash particle aggregation on electric charge presents a fascinating aspect of volcanic activity. When a volcano erupts, ash particles are ejected into the atmosphere, creating an environment ripe for electrical phenomena. As these particles collide and fragment, they accumulate charge through a process known as triboelectric charging. This interaction leads to the separation of electric charges within the ash cloud, where lighter particles may acquire a positive charge and heavier particles become negatively charged. The dynamics of these charged particles influence the overall electric field within the ash cloud. As aggregation occurs, larger clusters of charged particles can form, increasing the likelihood of discharge events. This process may lead to the generation of volcanic lightning, a striking visual display produced by the rapid release of energy between oppositely charged regions. And so, the electric discharges can also affect the trajectory of ash dispersal, altering how particles settle back to the surface. In regions where volcanic activity is prevalent, the resulting electric fields can create a complex interplay between ash movement and atmospheric conditions. Understanding these interactions provides insight into not only the immediate effects of an eruption, but also the long-term impacts on climate and air quality. Continued research in this area may reveal critical information about the mechanisms behind volcanic phenomena.
Volcanic lightning emerges as a fascinating intersection between geological activity and atmospheric electricity. This phenomenon occurs during explosive eruptions, when ash and volcanic gases create an environment conducive to electrical discharges. The intense heat generated by molten rock interacts with airborne particles, facilitating the buildup of static electricity. As these particles collide and aggregate, a discharge manifests, illuminating the ash-laden skies with fleeting bolts. The occurrence of volcanic lightning contributes to the broader concept of the global electric circuit. This system is essential for understanding how terrestrial and atmospheric electricity interact across vast distances. Charged particles from eruptions can influence local weather patterns, momentarily altering the atmospheric electrical balance. The energy released during these lightning strikes serves not only as a visual spectacle, but also as a significant contributor to the global electrical landscape. In volcanic regions, the presence of ash clouds alters the conductivity of the atmosphere, enhancing the potential for lightning creation. This dynamic interplay between the Earth's surface and its atmosphere underscores the intricate relationships that define our planet. While volcanic eruptions are localized events, their impact can ripple outward, influencing weather systems and electrical behavior far beyond their immediate vicinity. Understanding these connections may provide insights into both volcanic activity and the broader electric circuit that envelops the Earth. The intersection of volcanology and atmospheric science reveals intricate interactions between geological and atmospheric phenomena. Volcanic eruptions release vast amounts of ash and gases into the stratosphere, creating both immediate and long-term effects on weather patterns and climate. These eruptions can inject sulfur dioxide high into the atmosphere, where it converts to sulfuric acid droplets, leading to cooling effects that can persist for years. This region, laden with ash, becomes an active participant in the electric circuit, connecting the Earth's surface to the upper atmosphere. Particles within the plume collide, generating static electricity, which can manifest as lightning. Such phenomena have been observed during numerous eruptions, where the energy release is both visually striking and scientifically significant. The dynamics of these ash clouds can influence local meteorology, altering precipitation patterns and cloud formation. The presence of particulate matter impacts atmospheric stability, potentially enhancing or suppressing storm development. Understanding these relationships allows scientists to predict not only the immediate effects of eruptions, but also their long-term implications on climate variability. Research into these interactions continues to evolve, incorporating advanced satellite observations and computational models. By merging the disciplines of volcanology and atmospheric science, a more comprehensive understanding of Earth's complex systems emerges, shedding light on the delicate balance sustained within our planet's atmosphere. Changes in climate patterns influence the frequency and intensity of volcanic eruptions, linking warmer global temperatures to geological activity. This region of heightened volcanic activity often exhibits a correlation with rising atmospheric temperatures, prompting alterations in magma dynamics. Elevated heat can enhance the melting of ice caps and glaciers, resulting in increased water flow into volcanic systems. The introduction of this water into hot magma chambers can lead to explosive eruptions as steam pressure builds rapidly. The interaction between geothermal heat and the hydrological cycle plays a critical role in eruption dynamics. When water enters a magma chamber, it rapidly converts to steam, expanding and fracturing surrounding rock. This process can lead to significant eruptions, releasing ash clouds that can reach high altitudes. The ash particles themselves may carry electrical charges, generating volcanic lightning. a phenomenon that underscores the complex interplay between geological and atmospheric processes. In regions with historically active volcanoes, scientists monitor temperature fluctuations and precipitation patterns closely, as these shifts can serve as precursors to future eruptions. The implications of climate change extend beyond immediate volcanic activity, influencing broader environmental systems. This ongoing interaction raises questions about the resilience of ecosystems affected by both volcanic activity and climatic shifts, revealing the intricate connections that define Earth's systems. The presence of volcanic lightning introduces an additional layer of complexity to the already volatile environment surrounding an eruption. Within the billowing ash clouds, static electricity can accumulate, leading to powerful discharges that illuminate the sky. These surges of energy possess the potential to ignite dry vegetation in the vicinity, setting off wildfires that can rapidly spread across the landscape. The interaction between ash-laden air and moisture plays a crucial role in this process. When the ash particles collide, they generate friction, resulting in the buildup of electric charge. Once the threshold is reached, a lightning strike can occur, releasing energy that can be more than sufficient to kindle combustible materials. This phenomenon contributes to a feedback loop. As wildfires burn, they release additional particulates and gases into the atmosphere, further influencing local weather patterns. In regions where ecosystems have evolved alongside volcanic activity, the flora and fauna may adapt to this unique duality of destruction and renewal. Some plant species, for instance, have developed fire-resistant traits, allowing them to withstand the onslaught of flames. The aftermath of such wildfires, while devastating in the short term, can eventually lead to increased biodiversity as new growth emerges in the nutrient-rich soil left behind. This cyclical relationship underscores the profound interdependence of atmospheric phenomena and geological forces. Volcanic lightning manifests in the turbulent clouds of ash and gas that billow from erupting volcanoes. This phenomenon occurs when the ash particles collide, generating static electricity. The discharge can create spectacular displays of lightning, illuminating the darkened skies above. While visually striking, these lightning strikes pose significant hazards to aviation. Aircraft flying in or near erupting volcanoes are at risk of encountering ash clouds, which can severely impact engine performance. The presence of volcanic lightning complicates the situation, as it often indicates intense volcanic activity, suggesting that the ash concentration could be dangerously high. Pilots may find themselves navigating through unpredictable and rapidly changing conditions, where visibility is greatly reduced and equipment can become compromised. Air traffic control systems monitor volcanic activity closely, issuing advisories and rerouting flights when necessary. The dynamic nature of an eruption means that conditions can shift unexpectedly, requiring constant vigilance. Volcanic ash can lead to engine failure, and lightning may also pose a direct threat to aircraft structures. Precautionary measures have been developed, including specific flight altitude recommendations and enhanced real-time data sharing among aviation authorities. The interaction of geological eruptions and atmospheric electricity exemplifies the complexities of Earth's systems, highlighting the ongoing need for research and understanding in the field of aviation safety. Numerical models serve as vital tools in simulating volcanic lightning, providing researchers with insights into the intricate processes that govern these phenomena. By employing equations that describe fluid dynamics, thermodynamics, and electrical discharge, scientists can replicate the conditions found within ash clouds during eruptions. These models take into account various factors, including particle size distribution, ash concentration, and the temperature gradients present in the atmosphere. Simulation results indicate that interactions between volcanic ash particles and moisture lead to the charging of particles, which subsequently facilitates the generation of lightning. The models can predict the frequency and intensity of lightning strikes based on varying eruption scenarios, allowing for enhanced preparation and response strategies. They also assess how environmental conditions, such as wind patterns and humidity, influence the behavior of these electrical discharges. Ongoing advancements in computational capabilities enable increasingly complex simulations, incorporating real-time data from satellite observations and ground-based measurements. Such integration enhances accuracy, leading to more reliable predictions of volcanic activity and lightning occurrences. The findings from these numerical explorations contribute to a deeper understanding of the underlying physics at play, paving the way for improved safety measures in aviation and surrounding communities. Continued research in this domain remains essential for mitigating risks associated with volcanic eruptions and their atmospheric impacts. The interaction between volcanic eruptions and climate change reveals complex dynamics within Earth's systems. Eruptions release vast quantities of ash and gases into the atmosphere, including carbon dioxide and sulfur dioxide, which can have significant climatic effects. This region, often engulfed in a dense plume, can experience short-term cooling due to the reflection of sunlight by volcanic aerosols. The particles remain suspended for extended periods, altering local and global climate patterns. Sulfur dioxide, in particular, transforms into sulfate aerosols, contributing to a phenomenon known as volcanic winter. These transformations can lead to reduced temperatures, impacting agricultural systems and ecosystems. The lingering effects of an eruption can be profound, with evidence suggesting that historical eruptions have triggered periods of climate instability. Conversely, the role of climate change in influencing volcanic activity is also a subject of investigation. Alterations in glacial cover and increased pressure on magma chambers may affect eruption frequency and intensity. This feedback loop exemplifies the intricate relationship between geological and atmospheric processes. Understanding this interplay is critical, as it informs predictions about future volcanic events and their potential consequences. The continuous study of these phenomena holds relevance not only for forecasting eruptions, but also for comprehending broader environmental changes, driven by both volcanic activity and climate change.
The ash produced during volcanic eruptions plays a significant role in modifying local and regional weather patterns. When ejected into the atmosphere, particles can influence cloud formation, precipitation, and even temperature. This region, filled with ash, creates a different microclimate, as the fine particles serve as nuclei for cloud droplets, affecting the process of condensation. With the introduction of ash into the atmosphere, sunlight is partially obstructed, which can lead to cooling effects in the immediate vicinity. This phenomenon can disrupt normal weather patterns, altering precipitation rates and distribution. Studies have shown that areas downwind of erupting volcanoes often experience changes in rainfall, characterized by either increased intensity or prolonged droughts. The interaction between volcanic ash and atmospheric moisture is complex. Increased ash concentration can lead to the formation of heavier, moisture-laden clouds, resulting in intense rainfall. Conversely, in some cases, the presence of ash might inhibit rainfall, creating arid conditions. These variations can have cascading effects on ecosystems, agriculture, and water resources. Understanding the dynamics of ash clouds is critical for predicting the implications of eruptions on local weather systems.
Ongoing research into these interactions continues to unveil the intricate relationships between volcanic activity and atmospheric processes. Urbanization plays a significant role in shaping the landscape of volcanic lightning research. The expansion of cities often leads to increased monitoring capabilities as researchers install advanced detection systems and observation networks within urban environments. This accessibility facilitates a more comprehensive study of the phenomena, as densely populated areas can provide valuable data on the frequency, intensity, and characteristics of lightning events associated with eruptions. As urban areas grow, the interplay between natural and artificial light sources complicates the analysis of volcanic lightning. Ambient light pollution can obscure observations, making it challenging to discern specific events within the ash clouds. Researchers must account for these variables when interpreting data, leading to the development of sophisticated algorithms designed to filter out extraneous light interference. In addition, urban infrastructure can influence the behavior of charged particles within ash clouds. The presence of buildings and other structures can create localized effects on wind patterns and electrical fields, potentially affecting the generation of lightning. Consequently, understanding these dynamics becomes crucial in predicting lightning occurrences and assessing the associated hazards. This research is complemented by collaborations between volcanologists and urban planners, who aim to develop strategies for mitigating risks posed by volcanic eruptions in populated areas. By integrating scientific study with urban development, the understanding of volcanic lightning continues to evolve, highlighting the intricate connections between human activity and natural phenomena. Research into volcanic lightning is witnessing a gradual shift, driven by advancements in technology and interdisciplinary collaboration. Innovative imaging techniques are allowing scientists to capture the elusive electrical discharges within ash clouds with unprecedented clarity. High-speed cameras, for instance, reveal the intricate patterns of these phenomena, providing valuable data on the dynamics of volcanic eruptions. This region of scientific inquiry is becoming increasingly important as urbanization expands into areas prone to volcanic activity. Simultaneously, atmospheric modeling is enhancing the predictive capabilities surrounding these events by integrating meteorological data with volcanic activity. Researchers are developing more accurate forecasts of lightning occurrences. This fusion of disciplines is critical, given the potential hazards posed to aircraft and local communities. The development of advanced sensors is further contributing to real-time monitoring systems. These instruments can detect electrical activity within ash clouds, offering immediate insights into eruption behavior. The importance of understanding volcanic lightning extends beyond mere observation. It informs risk assessment and management strategies essential for protecting lives and infrastructure. As this area of study evolves, the potential for new discoveries grows. Continued funding and support for research initiatives will ensure that knowledge expands, fostering a deeper comprehension of the complex interplay between natural forces and their implications for society. The connection between volcanic ash and human health has drawn increasing attention in recent years. Fine particulate matter, often released during an eruption, can infiltrate the respiratory system, leading to various health complications. These particles, small enough to bypass defenses in the airways, may cause irritation and exacerbate pre-existing conditions such as asthma and chronic obstructive pulmonary disease. Prolonged exposure to ash can result in more severe respiratory issues, including reduced lung function and increased susceptibility to respiratory infections. This phenomenon is particularly concerning in densely populated areas where eruptions occur. The dispersion of ash clouds can blanket communities, enveloping them in a hazardous environment. Monitoring these ash clouds is essential for public health. In some instances, the ash may also contain toxic compounds, which further complicate the risk assessment. Heavy metals and other harmful substances can leach into the environment, potentially contaminating water supplies and agricultural lands. Studies have shown that populations living near active volcanoes often experience heightened rates of health problems following eruptions. Preparedness and response strategies must incorporate health considerations to mitigate these risks effectively. Understanding the intricate relationship between volcanic activity and public health remains a crucial endeavor as scientists strive to protect communities from the far-reaching consequences of such natural events. Community preparedness plays a vital role in mitigating the effects of volcanic eruptions. By fostering awareness and establishing proactive measures, local populations can significantly reduce risk. Educational campaigns inform residents about the signs of impending activity, including seismic events and changes in gas emissions. These initiatives promote vigilance, ensuring that communities remain alert during potential threats. Emergency response plans are central to effective preparedness. Designated evacuation routes and safety zones are established, providing clear guidance for residents. Drills and simulations reinforce these plans, allowing individuals to practice their responses in a controlled environment. This familiarity can save lives during an actual eruption, as chaos often accompanies natural disasters. Local governments collaborate with geological experts to monitor volcanic activity. Data from seismic monitoring stations and satellite imagery enhance understanding of potential hazards. Timely information enables authorities to issue warnings, ensuring that communities have the necessary time to prepare for evacuation if required. An engagement with local populations fosters resilience. Community leaders often play a crucial role in disseminating information and coordinating resources. By building trust and open lines of communication, these leaders ensure that residents are informed and prepared, reducing anxiety associated with volcanic threats. And in this context, the strength of community bonds becomes evident amid as collective action enhances overall safety and preparedness. These measures, rooted in collaboration and awareness, the importance of interdisciplinary research in understanding volcanic lightning cannot be overstated. This phenomenon, often occurring during explosive eruptions, involves complex interactions between volcanic gases, ash particles, and atmospheric conditions. It is within these unique environments that static electricity builds, creating the dramatic displays of lightning weaving through ash clouds. Meteorologists contribute critical insights into atmospheric dynamics, investigating how wind patterns and moisture levels influence the development of these electrical phenomena. Geologists, on the other hand, analyze the composition of volcanic materials, revealing how different ash types and sizes affect charge generation and discharge processes. The collaboration of these disciplines fosters a comprehensive understanding of the mechanisms underpinning volcanic lightning. Expertise in electrical engineering further elucidates the behavior of electric fields in these turbulent settings, providing models that predict the occurrence and intensity of lightning strikes. It is this synergy between diverse fields that enhances predictive capabilities, which field studies, combining remote sensing technologies and ground-based observations, enable researchers to collect valuable data on volcanic activity and associated lightning events. This multifaceted approach to research not only advances the scientific community's understanding of volcanic lightning, but also aids in developing effective monitoring systems to safeguard communities living in proximity to active volcanoes. The significance of volcanic lightning extends beyond mere observation. influencing our understanding of Earth's geological history. This phenomenon serves as a reminder of the dynamic processes shaping the planet. When magma rises and interacts with water, gases, and ash, it generates an environment conducive to electrical activity. The release of charged particles during explosive eruptions creates a network of lightning within the ash clouds, illuminating the sky with transient flashes. Such electrical discharges are not merely aesthetic. They play a crucial role in the atmospheric chemistry during eruptions. The reactions facilitated by these strikes can lead to the formation of various compounds, impacting air quality and contributing to climate variability. The historical records of volcanic eruptions, coupled with observations of lightning events, allow scientists to reconstruct past geochemical cycles and climatic conditions. In ancient times, these electrical displays were often interpreted through the lens of mythology, influencing cultural narratives and practices. Their presence during significant eruptions could have served as both a warning and a spectacle. Modern studies of volcanic lightning have provided a means to link geological activity to atmospheric phenomena, revealing patterns that help forecast future eruptions. This intricate relationship between electrical activity and volcanic processes enhances our comprehension of Earth's ever-evolving landscape, marking a critical intersection of geology and atmospheric science. Machine learning algorithms play a pivotal role in predicting volcanic lightning events, utilizing vast datasets of historical eruptions and atmospheric conditions. By analyzing patterns within these data, it becomes possible to identify the specific circumstances that lead to electrical discharges during volcanic activity. This technology harnesses the power of computational algorithms to sift through complex variables, including ash particle size, eruption height, and meteorological conditions. These models are trained to recognize subtle signals within the chaotic environment of an erupting volcano. They leverage real-time data from satellites and ground-based sensors, processing information about ash plumes and their interactions with atmospheric electricity.
In this region, the presence of charged particles can be correlated with the likelihood of electrical activity, allowing for more accurate forecasts. As the models refine their predictive capabilities, they offer invaluable insights for both scientists and emergency management teams. The ability to anticipate volcanic lightning enhances public safety measures, providing advanced warnings that can help mitigate hazards associated with eruptions. Analyzing the interaction between ash clouds and atmospheric electricity contributes to a deeper understanding of the complex dynamics involved in volcanic systems. This integration of machine learning into volcanology represents a significant advancement in the field, underscoring the potential for technology to enhance our understanding of natural phenomena. The emergence of citizen science has transformed the landscape of volcanic monitoring, presenting an opportunity for communities to engage actively with their environment. Local populations often possess invaluable knowledge about their surroundings, providing a unique perspective on volcanic activity. This grassroots involvement harnesses the power of crowdsourcing, enabling the collection of data from multiple viewpoints, which enriches scientific analysis. Platforms designed for citizen participation allow individuals to report observations such as ashfall or seismic events. These contributions are critical, particularly in remote or under-monitored regions. By sharing real-time information, citizens enhance the situational awareness of volcanologists, aiding in the early detection of potential eruptions. This collaborative effort fosters a symbiotic relationship between scientists and communities, as both parties benefit from shared insights. Technological innovations such as mobile applications and social media, further facilitate this exchange of information. They allow for the swift dissemination of alerts and updates, ensuring that communities remain informed about potential hazards. This proactive approach to monitoring can mitigate risks associated with volcanic eruptions. The integration of citizen science into volcanic research illustrates a progressive shift in how data is gathered and analyzed. It highlights the importance of community engagement in fostering resilience and preparedness in the face of volcanic threats. Geothermal energy emerges as a direct consequence of volcanic activity, harnessing the heat generated beneath the Earth's crust. This phenomenon occurs in regions where molten rock or magma rises close to the surface, creating a reservoir of thermal energy. These areas, characterized by high temperatures and pressure, are pivotal for energy production, offering a sustainable alternative to fossil fuels. The intricate relationship is evident in geothermal fields, where steam and hot water escape through fissures, providing a natural resource for electricity generation and heating. Harnessing this energy involves drilling deep wells to access the steam or hot water, which is subsequently utilized to drive turbines. The efficiency of such systems is bolstered by the constant supply of heat from volcanic sources, ensuring a reliable energy output. In addition to energy production, these geothermal systems often contribute to the local ecosystem, supporting a unique array of flora and fauna adapted to extreme conditions. The presence of volcanic activity fosters a diverse habitat, emphasizing the interconnectedness of geological processes and ecological balance. Monitoring geothermal energy extraction is essential as it requires careful management to prevent depletion or adverse environmental impacts. The potential for innovation in this field remains significant, offering promising solutions to meet growing energy demands while minimizing ecological footprints. Volcanic lightning serves as a crucial indicator of the various phases of an eruption. This phenomenon occurs when volcanic ash particles collide, generating static electricity that, during the initial stages, small bursts of lightning may appear, indicating the ascent of volcanic gases and fine ash. As pressure builds within the magma chamber, the frequency and intensity of these electrical events increase. This correlation allows researchers to estimate the potential scale of an eruption. Each flash illuminates the ash-laden sky, a fleeting glimpse into the chaotic forces at play within the Earth's crust. The intricate relationship between volcanic activity and lightning also aids in the understanding of eruption dynamics. Analyzing the characteristics of these electrical discharges, such as their duration and brightness, contributes to models predicting volcanic behavior. Such insights not only enhance safety measures for nearby communities, but also deepen the comprehension of eruption processes. This interplay of forces exemplifies the complex interactions within the planet's interior, where ancient powers continue to shape the surface. The resulting phenomena extend beyond geological impacts, influencing the very fabric of societies in proximity to volcanic activity. Communities have long been shaped by their relationship with these powerful natural events, often determining settlement patterns and agricultural practices. The threat of eruptions necessitates preparedness and resilience, compelling populations to develop comprehensive emergency response strategies. Volcanic lightning adds another layer of complexity. It signifies not only the intensity of an eruption, but also serves as a harbinger of potential hazards. Observations reveal that the presence of electrical discharges can impact air travel significantly, leading to the rerouting of flights and the cancellation of transport plans. Economic ramifications manifest as disruptions ripple through supply chains,
affecting local and regional markets. Cultural interpretations also arise, framing these events within myths and legends that reflect humanity's attempt to find meaning in their environment. Societies may view volcanic activity as both a destructive force and a source of fertility, as ash enriches soil, providing sustenance for future generations. The duality of destruction and renewal fosters a deep connection to the land, allowing communities to navigate the challenges posed by their volatile surroundings. In understanding these dynamics, one can appreciate the intricate balance between nature's fury and human resilience, revealing the enduring relationship forged through centuries of cohabitation with these elemental forces. Artistic representation of volcanic lightning finds its roots in the awe and reverence inspired by such phenomena. Ancient civilizations often depicted these striking displays, interpreting them through their beliefs and mythology. They transformed the violent spectacle into symbols of divine communication, attributing the flashes to the actions of gods or spirits. Paintings and carvings from this period reveal how communities sought to capture the essence of this powerful event. In more recent history, artists have continued to explore volcanic lightning, reflecting on its beauty and terror. Photographers and filmmakers document these rare occurrences, revealing the delicate interplay between light and ash. The stark contrast of brilliant electric arcs against the darkened sky creates compelling visual narratives, showcasing nature's raw energy. Literature also serves as a medium for expressing the profound impact of volcanic lightning. Poets and writers have employed vivid descriptions to convey the emotional weight of these phenomena, often using them as metaphors for internal struggle or transformation. Each depiction, whether through brush, lens, or pen, encapsulates a moment of striking beauty amid chaos. Cultural festivals in regions prone to volcanic activity often incorporate representations of this natural marvel, celebrating their connection to the land. In this way, the legacy of volcanic lightning continues to inspire and evoke reverence, shaping the narrative of human existence intertwined with nature's power. The evolution of lightning research in volcanology has progressed through meticulous observation and advances in technology. Initially, scientists relied on anecdotal accounts and rudimentary instruments to capture the phenomenon associated with explosive eruptions. Over time, the integration of high-speed cameras and thermal imaging has provided unprecedented insights into the dynamics of lightning within volcanic plumes. This region of study has revealed that the interactions between ash particles and gases create a complex environment where static electricity can accumulate. Charge separation occurs as particles collide and break apart, leading to the formation of electrical discharges. Researchers have documented instances of volcanic lightning reaching impressive altitudes, illuminating ash clouds against the backdrop of a darkened sky. Analyses of eruption data have highlighted correlations between eruption intensity and lightning frequency. It becomes evident that explosive eruptions are often accompanied by a surge in electrical activity, offering clues to the processes occurring deep within a volcano. Scientists utilize radar and satellite imagery to monitor these events, enhancing their understanding of how such phenomena can affect climate and atmospheric conditions on a larger scale. This ongoing exploration not only expands knowledge within volcanology, but also contributes to broader discussions on atmospheric electricity and its implications for weather patterns. Each discovery adds a layer to the understanding of how volcanic activity shapes both the landscape and the atmosphere. Education and outreach play a critical role in mitigating the risks associated with volcanic activity. Communities situated near these geological giants rely on comprehensive knowledge to prepare for potential eruptions.
Awareness programs highlight the behaviors and signs of impending volcanic events, equipping residents with the ability to respond effectively. It is not merely about imparting information, it is about fostering a culture of safety and vigilance. Localized training initiatives often incorporate simulations that replicate volcanic scenarios, allowing individuals to practice evacuation procedures. This practical approach reinforces the importance of being proactive. Schools and community centers become hubs for disseminating up-to-date information regarding volcanic monitoring and emergency protocols, ensuring that the entire population remains informed. Scientific institutions collaborate with local authorities to develop accessible resources, translating complex geological data into formats that resonate with the greater public. Visual aids and interactive platforms enhance understanding, bridging the gap between experts and laypersons. Regular workshops and public lectures emphasize the significance of ongoing research in volcanology. They highlight how advancements in technology can enhance predictive capabilities. The interactions between volcanic ash and climate models reveal complex dynamics within the atmosphere. Ash clouds, composed of fine particulate matter, can influence solar radiation and temperature regulation. These tiny particles scatter sunlight, reducing the amount that reaches the Earth's surface. The resulting phenomenon can lead to localized cooling effects, impacting weather patterns and climate systems over time. Incorporating volcanic ash into climate models requires precision in understanding its physical and chemical properties. This region of study focuses on how varying ash compositions affect light scattering and absorption.
The ash's interaction with moisture in the atmosphere creates conditions conducive to the development of volcanic lightning, a phenomenon that can further complicate atmospheric dynamics. Models must account for the distribution of ash particles, which can be uneven due to wind patterns and eruption dynamics. These variations affect how long ash remains suspended in the atmosphere and its subsequent effects on climate. Research continues to explore the longevity of ash clouds, essential for forecasting their climatic impact. Ongoing studies emphasize the need for high-resolution data to improve model accuracy. These advancements are crucial for predicting climate responses to volcanic activity, providing insights into potential agricultural impacts, and informing disaster preparedness measures. The interplay of these elements underscores the intricate relationship between volcanic events and global climate systems. Advancements in volcanic monitoring technologies promise to enhance the understanding of these complex phenomena. Innovative tools, such as satellite-based remote sensing, provide real-time data on volcanic activity from a distance. This method enables scientists to observe changes in thermal emissions, ash plumes, and gas compositions without direct risk to personnel. Ground-based sensors complement satellite imagery, measuring seismic activity and ground deformation. These instruments are capable of detecting minute shifts in the Earth's crust, often providing crucial early warning signs of an impending eruption. The integration of data from various sources offers a more comprehensive view of volcanic dynamics, improving predictive capabilities. Machine learning algorithms are increasingly utilized to analyze vast datasets collected from different monitoring systems. By identifying patterns and correlations, these algorithms can assist in forecasting eruptions with greater accuracy. The refinement of these technologies enhances the ability to assess potential hazards. Public engagement with real-time data is also evolving. Mobile applications and online platforms disseminate monitoring information to communities at risk, fostering awareness and resilience in the face of volcanic threats. As these technologies continue to develop, they hold the potential to not only advance scientific research,
but also to protect populations living in proximity to active volcanoes. This integration of knowledge and technology marks a significant step forward in understanding volcanic behavior. International collaboration plays a crucial role in advancing the field of volcanology. Researchers and institutions across the globe unite to share data, expertise, and resources, enhancing the collective understanding of volcanic systems. This synergy allows for more comprehensive monitoring networks, integrating diverse perspectives and methodologies to address complex volcanic phenomena. Shared databases, often maintained by joint efforts, yield valuable insights into eruption patterns and associated hazards, while satellite observations provide real-time updates on ash plumes and gas emissions. These contributions become particularly vital during significant eruptive events, where timely information can inform evacuation procedures and mitigate risks to populations. Collaborative projects may include joint expeditions to active sites, where scientists gather crucial samples and conduct studies in tandem. This hands-on approach fosters a deeper understanding of the physical processes at play, ranging from magma generation to eruption mechanics. The exchange of knowledge also extends into training programs, where emerging volcanologists benefit from the experience of seasoned experts. Workshops and conferences provide platforms for discussing recent findings, promoting innovation within the field. This unified approach reflects a recognition that volcanic phenomena do not adhere to geopolitical boundaries. By working together, scientists can enhance predictive models. Indigenous knowledge plays a crucial role in understanding volcanic activity, offering insights that modern science often overlooks. Generations of communities living in proximity to these formidable geological features have developed a profound connection with their environment. They observe patterns in the behavior of the land and sky, noting the subtle signs that precede eruptions. These observations encompass not only the physical aspects, but also the spiritual significance of volcanic activity. Traditional ecological knowledge includes narratives and practices that have been passed down through oral traditions. Such wisdom provides context for interpreting the changes in the landscape, including shifts in animal behavior or alterations in vegetation that may signal impending eruptions. This knowledge often emphasizes the cyclical nature of volcanic events, recognizing that eruptions are part of a broader ecological system. Collaboration between scientists and indigenous communities fosters a more holistic approach to understanding volcanic activity by integrating traditional practices with contemporary scientific methods. Researchers can enhance their predictive capabilities. This melding of knowledge systems creates a richer understanding of the complex interplay between humans and their environment, allowing for more effective risk management strategies. In this region, respecting and incorporating indigenous knowledge not only preserves cultural heritage, but also strengthens community resilience in the face of natural hazards. The land itself becomes a teacher, revealing secrets through its rugged terrain and shifting dynamics. The interplay between volcanic lightning and soil fertility emerges as an intriguing aspect of this phenomenon. Electric discharge during eruptions generates intense heat, which ignites gases present in the ash clouds. These gases, primarily nitrogen oxides, undergo transformation under such extreme conditions, leading to the formation of nitrates. Nitrates serve as essential nutrients for plant growth, enhancing soil fertility in the aftermath of volcanic activity. In this region, the deposition of volcanic ash enriches the soil with minerals like potassium, phosphorus, and sulfur. When combined with the nitrogen compounds created by electrical activity, a nutrient-rich environment develops, promoting robust vegetation in the years following an eruption. This influx of nutrients stimulates a cycle of renewal,
allowing ecosystems to flourish amidst the remnants of destruction. Observations indicate that following significant eruptions, areas previously barren can transition into thriving habitats. The resurgence of flora not only revitalizes local ecosystems, but also contributes to carbon sequestration, aiding in climate regulation. In the long term, the interplay of volcanic lightning and fertile soil creates a unique equilibrium, demonstrating nature's ability to rebound and adapt. This synergy between destructive forces and regenerative processes highlights the complex relationships inherent within Earth's systems. The intricate balance between chaos and rejuvenation underscores the resilience of life, even in challenging environments. The connection between volcanic eruptions and tsunamis is rooted in the powerful interactions between geological processes. When magma rises through the Earth's crust, it can produce explosive eruptions that displace vast amounts of water, particularly when these events occur in or near oceanic bodies. This sudden displacement generates waves that can travel across entire ocean basins at remarkable speeds. The force of an eruption can create a series of waves known as tsunamis, which can vary significantly in amplitude and frequency. These phenomena are often characterized by a rapid increase in water level, followed by a violent retreat, altering coastal landscapes and affecting marine ecosystems. The potency of these waves is determined by various factors, including the size of the eruption, the depth of the water, and the geographical features of the surrounding area. In some cases, eruptions can cause underwater landslides, further contributing to the violent disturbance of water columns. Such interactions can amplify tsunami effects, leading to devastating impacts on coastal communities. The historical record documents numerous instances where volcanic activity has led to significant tsunami generation, revealing the intricate relationship between these geological forces. Ongoing research continues to explore this dynamic, enhancing our understanding of risk assessment and mitigation in vulnerable coastal regions. The relevance of volcanic lightning extends into the field of astrobiology, where the interplay of energy and organic compounds is of paramount interest. In the context of planetary atmospheres, the conditions that facilitate lightning during volcanic eruptions may mirror processes occurring on other celestial bodies. The production of complex organic molecules through energetic processes, driven by volcanic activity, holds implications for the origins of life. In this region, the electrical discharges associated with volcanic eruptions can generate a variety of prebiotic chemicals, contributing to the theoretical frameworks surrounding abiogenesis. Researchers speculate that similar mechanisms could occur on moons with active geological features, such as Europa or Enceladus. The presence of water and potential volcanic activity on these icy worlds may create environments conducive to the synthesis of essential organic compounds. This phenomenon serves as a reminder of the connections between geophysical processes and the potential for life beyond Earth. The generation of volcanic lightning may also provide a natural laboratory for studying atmospheric chemistry under extreme conditions. By analyzing the interactions of volcanic gases, ash particles, and electrical discharge, scientists can glean insights into the conditions that might foster life in extraterrestrial environments. Unraveling the mysteries of volcanic lightning thus enriches the broader understanding of life's potential and resilience in the universe, bridging the gap between terrestrial phenomena and astrobiological exploration. The ongoing mysteries of volcanic lightning continue to captivate researchers, prompting further investigation into its formation and implications. Ongoing studies aim to clarify the precise mechanisms that trigger electrical activity within eruptive events. Observations indicate that the interaction of ash particles and gases generates static electricity, leading to discharge phenomena that can illuminate the darkened skies above erupting volcanoes. Future research directions will likely encompass a multifaceted approach, involving advanced modeling techniques and enhanced observational tools. Satellite technology may play a crucial role, providing real-time data on volcanic eruptions and their associated electrical activity. Instruments capable of measuring electrical fields and ash dynamics will offer greater clarity on the relationship between volcanic eruptions and lightning production. Collaboration between geophysicists, meteorologists, and astrobiologists is essential for a comprehensive understanding of this phenomenon, as volcanic lightning can serve as an analog for atmospheric processes on other celestial bodies. Insights gained from Earth may inform the study of planetary atmospheres elsewhere in the solar system. With each study, the intricate interplay of geology, chemistry, and physics unfolds, revealing the complexity of volcanic processes. The quest to decode volcanic lightning stands as a testament to humanity's enduring curiosity, seeking to uncover the secrets of nature and its potential to inform our understanding of life beyond our planet.